In this video, let us look at the average velocity of a particle in motion. So start first by defining the property of motion here, average velocity. What is it? We're using V bar to represent average velocity because subsequently we'll talk about instantaneous velocity. The average velocity of a particle is defined as the rate of change of displacement. The rate of change of displacement. It is actually total displacement divided by the elapsed time. Like I mentioned in our previous example trying to differentiate between distance and displacement, if my final position during all my work is at this point, and maybe I started my motion from here, my actual displacement is simply the length from where I am finally to where I actually started from. So, this displacement divided by the elapsed time is what defines our what? Average velocity. In fact, average velocity can also be seen to be the velocity between 2 points in a space of what? Time. Mathematically, the average velocity of a particle is expressed by this equation we'll have here on the board. Like defined already, it is the displacement divided by what? Elapsed time. When talking about displacement, it's final position minus what? Initial position. Because this occur in a specific time, so it's divided by the time at that final position minus the time at that initial position. What happens if the position of a particle is defined as a time function? Let's assume that the position of that particle is given like, okay, x of t equal to 2t squared plus 5t minus 1. 2t squared plus 5t minus 1, something like this. And then you are required to calculate the average velocity between 2 times. Let's say the average velocity between 1 second and 3 seconds. How do you actually go about that? Using this position function. Is that okay? Because the function is not defined in terms of time. In that case, equation 4b works conveniently, where average velocity will now be equal to position at the final time. I chose to use t2 here, minus position at the initial time, then divided by the difference of the time, final time minus what? Initial. How do we actually arrive at this? Remember I said, imagine that the position function is given as a time variable here. Is that okay? And you're required to calculate the average velocity between, say, 1 second and 3 seconds. The t2 will be equal to what? 3 seconds, and then the t1 will be equal to what? 1 second. All you need to do, get a position at this time. So come to this position function, substitute 3 into wherever you see t there, solve and get a position at that time equal to 3 seconds. Again, go back to it, substitute time equal to 1 second for t there, and then solve and obtain the position of the particle at time equal to 1 second. Fix up the position that you got there, and then the difference in time. Sum it out and you get your average what? Velocity. Please take note that average velocity, we consider it when the details of the motion at any instant, at any particular time is not required. The example I gave here, you would remember that I mentioned when you are required to calculate the average velocity or the velocity between 2 times. Between 2 times. But if you're required to calculate the average velocity at a specific time, okay, to calculate the velocity at a specific time, you no longer use average velocity because in that case, the details of the motion is required. So don't forget this, okay? Average velocity is considered when the details of the motion is not required. And you usually get average velocity between what? 2 times. Velocity, we know generally, whether average or instantaneous, it is a vector quantity. So you can actually get negative or positive in your result. In the next video, we are going to consider instantaneous velocity. In the previous video, we talked about that velocity that is required when the details of the motion at a specific time is not necessary. In this video, we introduce the concept of instantaneous velocity. What do you do when you are required to determine the velocity of a particle at a particular time, at a particular instant? So the term instantaneous velocity comes into play. Now just imagine that word, instant, instantaneous. Of course, instantaneous is obtained from instant, that's at a particular time. So whenever you are dealing with motion and then the details of the motion at a particular time is required, please remember that what you use is no longer average velocity, but what? You use instantaneous velocity, which by definition, instantaneous velocity, which also is simply called velocity, is the average velocity between 2 points on the path in the instant that the elapsed time approaches zero. Imagine you have this path. The average velocity between these 2 points along this path in the limits that the elapsed time to take from this point to this point approaches what? Zero. This definition is actually a differential calculus definition where we introduce the concept of first principle. In this video, I wouldn't go into details. Alright? You can access our YouTube channel at Genius41, subscribe to it and turn on the notification bell so that when we upload the concept of differentiation from first principle and explain what it's all about, you will understand even more better the concept of the limit of a quantity approaching zero and how that translates into our total derivative, that is derivative of the function with respect to a given variable. Alright, now let's come back to what we are dealing with here. Like I mentioned earlier, when you're dealing with instantaneous velocity, that is when it is required to determine the velocity at a particular time, at an instant of time. This time around, not between 2 times again, where you are to determine the velocity when time is 5 seconds, when time is 2 seconds, you know. In such case, the position of the particle is given as a continuous function of time. Take note, the particle's position is expressed in this case as a continuous function of what? Time. That is where we usually encounter this term which I introduced in the previous video, x of t. Are you following? X of t. That is this position as a function of what? Time. Might be given equal to something, you have something like 2t squared plus maybe 5t, you know. You may just write anything to define the function for you. Does that make sense? When this challenge is given, the principle of calculus is used to solve the problem. Mathematically, we introduce the definition that the instantaneous velocity is equal to the limit of x t plus change in t. That is the limit of the position when there is an increment in time. Is that okay? Minus the position at any particular time divided by the elapsed time. And this limit is taken when the elapsed time approaches, tends towards to zero. Under limit in mathematics, we explain this concept of approaching, of tending to zero. Is that okay? Alright, now this definition from first principle translates into total derivative. Therefore, the instantaneous velocity is now given as d dt of x of t. What does this mean? You notice that I wrote this x of t in a different color. Okay, this is to tell you that this d dt, this differential coefficient d dt is an operator. It works on something. So in this case, this d dt is working on the position function. Are you following? That is the position of the particle. So this simply means differentiate with respect to time the position of the particle. You know, soon we'll introduce the concept of instantaneous acceleration, where in that case we'll be differentiating with respect to time the velocity of the particle. Is that okay? So please, equation 5, you need it very, very much, okay? You have to memorize that. This simply tells us that instantaneous velocity, also simply known as velocity, is the first time derivative of position of a particle. That is, if you differentiate the position of a particle with respect to time, what you are meant to get is what? Instantaneous velocity. In this video, we have this graph on the board we want to look at, make an interpretation to read, and then we make some conclusion from the graph. So this is the graph. The graph is position function graph. Is that okay? We plotted position against what? Time. Then you take note that we have these two important points, point A and point what? B. Yes, I say they're important with respect to calculus based on what I really want to explain here regarding instantaneous velocity. Point A is known as the maximum point of the function, and then point B is known as the minimum point of the function. Now you take note that at this point A, the time I've labeled it as t subscript 0, that's t naught. Then at point B, the minimum point also, I have t naught there. What happens there is very, very important. We know when you plot a graph, assuming that you plot a graph, you have something like this. You can actually take the slope of the graph. If it is a straight line graph like this, once you have any straight line point, you can take the slope this way. Is that so? But whereby the graph that you plotted, let's assume it's something like this, and then you have a straight line horizontally like this. This straight line touched this y-axis at this point, just one point there. Or you have this straight line that went up like this vertically, it touched the x-axis just at one point here. If you are to determine the slope of such line, is that okay? It's going to be equal to 0. For you to get a slope which will have a value, the line will not be purely horizontal or purely vertical. It must be an inclined line like this, so that you can get two different values on y-axis and on x-axis. Is that okay? That we can actually obtain from this point down to the point just before A. But at this point just before A, once you move to this point A, the slope at this point will be equal to 0. But from this point to the point just before A, you can actually get the value of the slope, which will not be 0. But once you get to this point A, because at this point A, if you are to draw the line that will help you get the slope, the line will be a purely horizontal line like this. And just like I explained here, the slope will be 0. The same thing at this point, what? B. So point A is maximum, point B is minimum. So from the graph at point A and point B, the slope of the graph is equal to 0. And slope of the graph is d dt of the position function. Because you know that slope is actually change in y over change in x. You remember that, right? Our y here now is x, the position. And then our x is what? T. So it's going to be change in x over change in t. That change now, according to the definition from first principle, is what we refer to as d. Okay, introduce that differential coefficient anyway. So d dt of the position function. So at this point A and B, the maximum and minimum points, this dx over dt is equal to 0. So take note of that, very important. Now, some notes that I brought out here we want to look at. Number one, the instantaneous velocity at any time in this graph would give us the slope of the position function. Take note of that. If you want to determine the instantaneous velocity, for this, all you need to do is to obtain the slope at any given point given to you. Like I stated, in instantaneous velocity, you'll be asked to calculate the velocity at any particular time. So this instantaneous velocity is the slope of the position function at that time that you're asked to calculate the instantaneous velocity. Point number two, when the position function is maximum or minimum, the slope is 0. And what's the implication? The first derivative of position, dx over dt, will be equal to 0. I stated that already in this equation here. Is that okay? So I've just emphasized it because that is very, very important. Don't worry, when we solve question, we'll find it. Okay, following from point 2 above, it therefore means that the zeros, also known as the root of the velocity function, the instantaneous velocity, its zeros, its roots. Under polynomial, there's something called the zeros of an equation or the root of an equation. In quadratic equation, you heard that. Is that not so? So the zeros of the velocity function occurs at the minimum and the maximum point of the position function. So just imagine you're given a question and then you are asked to obtain the zeros or the root of the velocity function. It occurs at this point A and point what? B. And all you need to do is to take the derivative of the position function equal to 0 and then solve. Is that okay? You solve and obtain the values of the velocity, the zeros, the root of the equation. Of course, in that case, it will give you a polynomial of degree 2 and above. Okay. Point 4. The minimum or maximum point of the position function is the stationary, the turning, or the critical point of the position function. An examiner may just dribble you into, okay, fine, what is the value of the time during which the particle's position is stationary? That is to say, the particle is not moving. You should calculate the time there. How do you go about that? You want to recall that at stationary point, at turning point, also known as the critical point of the position function, that you refer to that as the minimum or the maximum point of the position function. And like I stated, the minimum and the maximum point is at that point that we obtain the zeros of the polynomial or the zeros of the velocity function. So all you need to do is simply do your differentiation and then make it equal to what? 0. Solve whatever you get there as the equation. So this is extremely important. You use it when talking about stationary point, when talking about the maximum or minimum point of the given position function. In this video now, we want to look at speed and average speed, another property of motion, alright, quite closely related to velocity. But what is speed? With speed, we can talk about it in terms of average and in terms of instantaneous speed, just like we had previously, average velocity and instantaneous velocity. So we start by defining average speed first. Average speed is simply defined as the rate of change of distance. It is actually the total distance divided by the elapsed time. I've chosen to use S bar to represent average speed. Mathematically, equation 6 defines average speed for us. Say it's total distance, and simply distance divided by the elapsed time. Now, the concept of average speed and average velocity sometimes can be confusing, especially if the motion is a one-step motion. Is that okay? Because just like we try to differentiate between distance and displacement, and we stated that in a one-step movement, distance and displacement are equal. The same thing with average speed and average velocity. In a one-step movement, is that okay? One-step motion, the average speed and average velocity mathematically will give you the same result. And that is why there are certain cases that we even use these two interchangeably, the hearing speed, velocity, in the same concept. But they are not exactly the same when you come into physics. Is that okay? Average speed, or simply speed, generally is a scalar quantity and velocity is a vector quantity. But now let us look at a real life situation to help us see another clear difference between average speed and average velocity. We shall consider an athlete that is running. Imagine an athlete is running, is that okay? And then the athlete moves from point A to point B, and the distance between A and B is 50 meters. If the athlete runs from point A to point B, this athlete had covered 50 meters. Just in that one-step motion, if you calculate the average speed, you will get the same result as the average velocity as well too. But now, to help us understand the difference between the average speed and average velocity, let us consider that the athlete now ran back from point B to point A. From A to B is 50, so moving from B back to A will still be 50 meters. In this situation, average speed and average velocity are no longer equal. How so? If you talk about the average velocity in this case, remember average velocity is displacement over what? Time. And displacement, they change in this position and running from here to this place 50 meters and then coming back. By displacement, you need to introduce sign. Coming back will be minus 50. So if going is plus 50, coming back is minus 50, the total displacement will give you 0. Which simply means that the average velocity in that case will give you 0 because the displacement there is 0. Average velocity is displacement over time. So if displacement is 0, they expect that the average velocity will also be what? 0. But in the case where this athlete ran back from point B to point A, is the average speed 0? The answer is no. The average speed is not 0. The reason is this: total distance divided by what? Time. The athlete ran A to B, 50, B to A, still 50. The total distance is 100. So it's going to be 100 divided by the given time, which of course is not 0. So take note of this, please. That is a classical or a real life difference between what average speed is and what average velocity is. Now I want to look at instantaneous speed, another form of speed. That speed considered at any instant of time. Remember, average speed is considered between two times, alright? Instantaneous speed is simply the magnitude of instantaneous velocity. And you recall that instantaneous velocity is the velocity at any given time. Is that not so? So once you get the value of that instantaneous velocity, the instantaneous speed is the magnitude of that instantaneous velocity. Now take note, instantaneous velocity can either be positive or negative as a vector quantity. Instantaneous speed is always positive. Take note of that. So for example, if you calculate instantaneous velocity and you get something like -3, then the instantaneous speed will be magnitude, the absolute value of that -3, which of course will give you what? +3. In this video, we now give attention to the average acceleration and the instantaneous acceleration, another property that describes motion in kinematics. So what is average velocity? What is instantaneous velocity? First, we start by looking at average velocity, and it is defined simply as the rate of change of velocity. Is that okay? Mathematically, it is given as velocity at a given time, final time minus velocity at initial time divided by the elapsed time. That is final time minus initial time, you know. So you see the numerator, just change in velocity divided by change in what? Time. Now I want to look at instantaneous acceleration. That acceleration at a particular time, at an instant of time. The instantaneous acceleration is defined as the limit of average velocity as the elapsed time approaches 0. You see, this definition is similar to that of instantaneous velocity, is that not so? Because when we talked about instantaneous velocity, it is actually the limit of displacement. Is that okay? As the change in time, that is the elapsed time, approaches what? 0. Alright, now having known that instantaneous acceleration is actually the limit of average velocity as the elapsed time approaches 0, it simply means we can actually write equation 8 in a form of first principle of differentiation, that is differential calculus, and then we will now translate the instantaneous acceleration to a concept of d dt. Is that okay? And that is what we actually have here. If you take the limit of this velocity as the elapsed time approaches 0, the instantaneous acceleration will now be d dt of the velocity function. Is that okay? That is, you're meant to take the time derivative of the velocity function. Once again, all this concept is similar to what you saw under instantaneous velocity. The only difference is that there you were dealing with velocity, which you obtain from position, displacement, you know. But acceleration, you are now obtaining it from velocity. So take note of this equation 9 start this equation 9, let me start it very important. So whenever you're given velocity function, differentiate it once. What you get is the instantaneous acceleration function. Now we know the velocity function to be the first time derivative of position. Velocity, that is instantaneous velocity, is d dt of x of t, where this x is the position function of whatever particle you're dealing with. Is that okay? Therefore, we try to see how we can obtain the instantaneous acceleration as a function of position. Take note, according to equation 9 star, it's telling us that instantaneous acceleration is the first time derivative of what? Velocity. Now, if in place of this velocity, we impute what we know about velocity before, that velocity is the first derivative of position with respect to what? Time. We are going to get the acceleration to be equal to d dt, you can see that. Then in place of this velocity, we'll now impute this value, d dt of x of t. Is that okay? d dt of x of t. Now, if you open up this bracket, you would notice something now. That d dt of x of t, this d dt is this one, that is derivative with respect to time, this first one. Then velocity on its own has derivative with respect to time of position. Now if you open up this bracket and multiply, this dd will give us d2. Is that okay? D2, that's how it's pronounced, although some persons simply pronounce it d squared. But it's called d2. Is that okay? So d2 all over, then dt times dt will give us dt squared. This is d2 of x of t. Now what's the meaning of this? d2 of x of t, then dt squared. It simply means that you should differentiate twice with respect to time the position what? Function. If you differentiate the position function 2 times in respect to time, what you're going to get is what? Acceleration. So do you see, besides acceleration being the first time derivative of velocity, acceleration is also the second time derivative of what? Of displacement. That is of the position function. Now we've established this, so these two equations, 9 star and then 10 star, very, very important. Then coupled with this equation 8. Please take note, you can put this down. The third time derivative of position, that is if you differentiate position 3 times, you get a quantity that is called the jerk. In the next video, we're going to take questions on these and then we solve to see how we apply the average acceleration and the instantaneous acceleration using what we've established here on the board. After which, we'll now consider how this can be translated to integration. Because if acceleration is first time derivative of velocity, I can obtain velocity from acceleration by integrating acceleration. The same thing, when we have velocity to be equal to the first time derivative of position, it means I can obtain position by integrating velocity. So we're going to see all those in the subsequent videos.